Hello viewers, thanks for watching. So in this video we're going to consider vector projection. So here we have two vectors v and vector w, and we can see that there's an angle between the two vectors, and then we are interested here to know the fact that if theta here is reducing from, let's say, from 45 to 40, from 40 to 30, from 30 to 20, from 20 to 5. So as this theta is reducing, angle v, vector v, will be coming down to stand on vector w exactly. So if that is the case, then we want to know the fact that what would be the gap, what would be the distance that this vector v will cover on vector w. But this time around, we need to find it in terms of its magnitude and direction. Okay, so that's what we call vector projection, compared to scalar projection, that if something like that is going to happen, we only want to know the magnitude. We only want to know the magnitude that vector v will cover on vector w. Vector v will cover on vector w. We only need to know that. Okay, so in that case, we now want to go straight to the business, which means that we want to consider the definition. And the definition here is that the vector projection of v on w will give us v dot w over magnitude of w, or multiplied by w over magnitude of what? Of w. I mean vector w over magnitude of vector w. So that will give us the vector projection. So here now we have the gap here. We have the gap here. You can see here, which is the distance, that vector v will be on w. Okay, but do you notice something here is that on w we have it to be magnitude of w, magnitude of w. That's why sometimes they say that dot product between the two vectors multiplied by the vector divided by the square of the magnitude. That is what they are trying to say, which means they are also correct. So let's consider this example. So let's consider this. So find the vector projection of A, which is 1 and 2, on another vector B, minus 1 and 1. You know, you are familiar with this question. We've obtained the scalar projection in the first video. Okay, so this time I want to find the vector projection. So what do? Dot product over magnitude of B. Remember that on B is saying the projection is on B, the vector A is on B. Okay, so we have it magnitude of B, then this is the dot product, this is vector B, then this is the magnitude. So, okay, so when you do that, you see that 1 times minus 4 will give us minus 4, 2 times 1 will give us 2, the minus 4 square will give us 16, 1 square will give us 1, then the square root will be 17. Then likewise we have this, which is minus 1 and 1 over square root of 17. So if you do this very well, you see that root 17 times root 17 will give us 17, and then minus 4 plus 2 will give us minus 2. So minus 2 here times minus 4 will give us 8. Minus 2 here times 1 will give us minus 2. So this is the vector projection of vector A on B. So let's look at the interpretation now. Look at it. This vector, it is vector B. Okay, but we are dealing with A on B. So look at it now. This is A on B here. We need to stretch it backward. We stretch it backward. So we have A on B. But assuming that we want to do B on A, so we stretch it to the other side. Are we together? We stretch to the other side. Then if you stretch it from here, then you now see that we can have B on A. Okay, but here we are dealing with A on B. This is the other side of B. This is the other side of B. But remember this condition as well, that here there must be angle 90 degree. Here must be angle. The projection, okay, it must stand in such a way that there will be 90 degree. So let's look at question number 2. We are given vector A here, which is 3 dimensions, ijk. So we have vector A to be A 1 minus 2. We have vector B to be minus 1 0 and 3. So we want to find the vector projection of A on B. Okay, of A on B. So we have it, remember, on B. We don't know the angle between them. Of course, we don't know the angle. So we deal directly with the dot product. We find the dot product. We find the magnitude of B. So we have vector B over magnitude. So just like I've explained earlier, to find the dot product is very simple. That's 0 times minus 1 plus 1 times 0 plus minus 2 times 3. So we have b, which is minus 1, 0 and 3. Then we have the square root, which is this. So this is the square root of vector A, vector B, magnitude of vector B, magnitude of vector B. So we do it like that. So 0 times minus 1 will give us 0, 1 times 0 will give us 0, then minus 2 times 3 will give us minus 6. Then we have minus 1, 0, 3, minus 1, 0, 3, then divided by 1, 0 plus 9. So we do this together, then we obtain the vector, which is the projection of A on B. So the vector projection of vector B on A, what we want to do? No, the first question we solve is actually vector A on B. Now the second one is now vector B on A. So vector B on A, remember this, we have this expression dot product, then we have A, then we have the magnitude squared. So we do that. Now the third question is that, so the third thing now is that we want to find the vector projection of vector A onto unit vector K. And what is the unit vector K? Unit vector K is 0i, 0j and 1k. Okay, so here now we need to find the dot product between A and K. Okay, and that will give us, what is our vector A? Vector A is 0, that will be 0 times 0, then 1 times 0, then minus 2 times 1. Don't forget, unit vector K is 0i, 0j and 1k. So it's 0 times 0, 1 times 0, then minus 2 times 1. That will give us minus 2. Then the magnitude of vector K, that will be 0 squared plus 0 squared again, then plus 1 squared. And 1 squared is 1, the square root of 1 is what is 1. So we have the magnitude to be 1. So by the time you do that, we have the vector projection of vector A onto a unit vector K to be this. Then let's look at this problem again. Question 4. We have 3i, vector A is 3i plus 4j, vector B is 2i minus j. So we want to find the vector projection of A on B. Vector projection of A on B. So we have this one, we don't know the angle. So we obtain this, which is the scalar projection. Then the scalar projection multiplied by the vector that is below, divided by the magnitude, which is what we are familiar with before. So that will give us 2 over square root of 5 multiplied by vector B, which is 2i minus j, divided by square root of 5. So this will give us the vector projection. So we are going to come to the end, but before then, let's always remember that the scalar projection will always give us the magnitude of the component, while the vector projection will always give us the actual vector component. Together, this will offer a comprehensive understanding of how one vector relates to another. This will help us to calculate the length, direction, and angle between the two vectors. Thank you very much for watching. Thank you. Bye.